Hi everyone. So once again, if you can just put in the chats if you can hear me just before we kick things off. Andre, Johan, welcome. Are you able to just put something in the chats if you can hear me? Thank you. All right. So welcome everyone. Thank you for joining us. So just before we kick things off, I just want to give you a few tips over here. So if you can go on your settings, you should be able to disable all the sound and the notification that might disturb you along the way as you're trying to listen to the session. So if you can disable that. All right, so welcome to our session today. The topic for today is data-centric evolving power grid, hosted by our professor, AK, who is also EIT Academic Board Deputy Chair. So before I hand it over to him, just common questions that they usually come in. So in terms of copy of the slides or the recording, you should be able to receive the PDF slides of this session and also the recording in the next 2 working days. And also with the certificate of attendance, we should be, I should be sharing a link or a QR code at the end of the session. So you should be able to complete a short survey form in order to request your certificate of attendance. Sorry, my system is still picking up the next slide. Yeah, so here just to give you an overview about EIT, more especially for those who are joining us for the first time. So yeah, EIT is a specialist in engineering. We specialize with engineering courses from professional development courses, advanced undergraduate, graduate certificates, bachelor's, master's, and then our higher engineering. At EIT, we are industry orientated, as you may agree that there's a lot of changes happening in terms of the industry itself. Job market is changing, so at EIT we ensure that our resources and as well as our materials are up to date, just to keep up with the trends. We are accredited with Australian government, just like any higher education provider in Australia, and we also have some of our programs that are international, that are recognized under 3 international engineering accords. We source our lectures from different parts of the globe. We use unique delivery method, interactive webinars to ensure that we make it easy when coming to studying with EIT for our students. So that being said, I'm just going to quickly jump into the next slide where I will hand things over to the professor. Please bear with me with the system.
Right. Good afternoon or good day to everyone. Khalil, can you hear me? Khalil now. Khalil, can you hear me? Can you let me know if you can hear me, Khalil? And others or anyone else who wants to respond. I want to check whether everyone can hear me. Thank you very much, Khalil. Thanks a lot, Rojin. And thanks a lot, everyone. And let's start. Thank you, John. Let's start our session. Today, I'm going to talk about something very interesting and something which has been bugging me for a long time, and that is on the data-centric smart grid that we have today. Before I start anything, I would like to mention to you one point, and that is that we have got a very smart grid, okay? And this market is ever evolving. And moreover, this market is becoming very, very difficult in present day with all the artificial intelligence that is going on and all the amount of data that you see in this market. I think it is becoming I think it is becoming more of an issue than anything else. I just wanted to mention to you some of the things that I think is a very important thing. One is that the market is new and the market is liberalized. We have got a lot of bulk power being transferred from one end to the other end. The customers no longer are customers, they are presumers. Presumers, for those who do not understand, they are not only customers of some electricity supply industry or companies, but they are also producing their own electricity and selling it back to the grid. So there's all sorts of things which is happening. We have got new storage technology, looking at about less than 100 megawatt. We're looking at non-conventional renewables. We are seeing more and more of onshore and offshore wind farm and PV. So there's storage of all sorts are coming in. And recently we are doing a lot of work on hydrogen too. So you must understand that this small scale, widely dispersed technology has become a very important thing in the distributed network. So now, if you let me erase this, so you can see that this has become a very important factor these days, and you'll be surprised, my friends, that we are looking at huge amount of proliferation of power electronics. The power electronics has come and completely changed the whole scenario, because with power electronics you find that the equipment sizes have definitely reduced, but they have brought in a lot of harmonics. Again, we find more and more HVDC coming in. So we find all these LCC, that is line commutated computation, or VSC type of technology coming in. So this whole super grid is meshed in such a way that the new things are making life very difficult for conventional power engineers. And you find again things like things like things like static and active, shunt and series compensation, more and more of flexible AC transmission. So you find that not only that, the load is also changing. So the customer's load is changing. You find heat pumps, power electronic load, new type of lighting, and a lot of them have got greater controllability. And on the top of this, we have got EVs, electric vehicles. I can tell you right now, electric vehicles is going to create quite an issue from 2035 onwards. As a matter of fact, in Australia, we are looking at 2050, there won't be any more IC engine. That's what the government wants to see. So from 2035 onward, more and more vehicles that we will find which are electric in nature. So this power network that I'm talking about is going to be with a lot of integration of ICT, and there'll be a lot of challenges. especially to get information out of this. There will be huge amount of integration of very intelligent power electronic devices, and you will see a lot of bidirectional flow. You will also see huge amount of energy carriers. You will see huge amount of energy carriers. And on the top of that, you also have this cyber security. So cyber security is another thing which is going to make a very big issue for all of us. So let us see the network. Let us see the network. In the past, I only had something to worry about, which was my electric power network. Now I've got comms network too, because the amount of communications which is required to transfer information from the generation to the load, from the control center to the load, from control center to generation, between customers. So huge amount of communication has come in. So with the power network, a new network has evolved, which is the comms network. And another network which we have forgotten completely is the gas network. So there are now, if you look at it carefully, there are three networks. The power network, which is the traditional electrical power network with all the transmission, distribution, generation, sub-transmission, the load. Along with that, we now have a comms, which is as big as a power network. And then we have this gas network too. So there's all this proliferation of the new type of networks which has come into the system. And if you look carefully, if you combine all of them together, that means looking at the smart building, smart city, looking at smart network, you find a completely a spaghetti network like that, where there will be a huge amount of smart cities there, smart networks there, smart grid there. So that is how complicated your network or your city or your building is going to be. So let us look at the idea itself of the power and energy network. First thing is that there is going to be variable power flow. So you're seeing this variable power flow. Okay. Your generation storage and the P that is connected, they are going to be uncertain. Then you find huge amount of P-based transmission facility technologies. I did use the word VSC, MCC, LCC, all these new type of HVDC devices coming into the system. Then you're also going to see both the temporarily and spatially varying and uncertain load. The load is very unpredictable, very uncertain, because as I told you, you are no longer only consuming electricity from your utilities, but you are also going to be seller of the utilities. The whole thing has become very complex. And you have got a huge amount of data. This huge amount of data is a huge problem. I do not know how to control my good data, my bad data, my ugly data. I, as a power engineer, have got huge amount of problem with this type of data that I am getting. And then the uncertainties have become so bad that my security has become a very big issue. And that security, my friends, you will find is a very big problem for the power sector today. So, if you look carefully, let us look at some threat, my friends. Let us look at some threats. Let's look at some threats. And if you look at the threats, in the olden days, I was only worried about accidents and technical faults. That's the only thing I was worried about. Okay. I always had this problem. I had extreme weather condition, natural disasters. You find nowadays it is becoming more acute. You sometimes hear about El Nino effect, El Nina effect. I don't know, all sorts of effect which is changing the climate, which is making your system very difficult to control. And then on the top of that, my friends, I have got cyber attack, malicious attack, and things like COVID has come in. So pandemics have become a very big issue. Today is COVID, tomorrow is something else. I don't know what is going to happen. So, but these things which are there, they are stochastic in nature, and they all impact our systems in a different manner. And many times this brings in disaster to our system. So if our system is not modeled properly, my friends, you will find huge issues with your system planning, operation, and control. So you're going to have a huge problem. And as a conventional power engineer, as I told you right in the beginning, as a conventional power engineer, I'm having difficulty with this. So let us look at the network and let us look at the resilience of this network. The first resilience is on the network, the second is on workforce, and the third is on the cyber. These are the resilience. The network itself, this is a classic resilience because we've got physical assets. You're going to have some resilience in the network itself. Workforce resilience. This is going to be a big problem because we will not have the trained and those workforce who have got appropriate training, who are available with appropriate skill to be able to run the system. And cyber resilience, as you know, every time we keep on getting ransomware, this way, that way, our data is not at all secure. Then, if you look carefully, we must have in such a way the power system itself must be resilient or must be able to withstand any disaster. And that is what we claim, that we should be able to do that. It should be able to withstand any disaster. And there could be two types of things. One could be low frequency, the other could be high impact incident. This will ensure, if I can do this efficiently, this can ensure the least interruption in my electricity supply. That's what we want, isn't it? We do not want blackouts and brownouts to be occurring. And if we can do this properly, we can sustain the critical social service and enable a quick recovery and restoration to the normal operation state. Remember, my friends, this power system is no longer Father Christmas, right? Please remember that if they lose few minutes of their supply due to whatever reason, they are losing dollars, my friend. Remember that dollar they are losing. So let us see what are the low frequency type of incident. They are the long-term monitoring data combined with probabilistic or forecasted evolution or evaluation of metrics. So the metrics could be the power or the energy is not supplied, the duration of interruption is not known, frequency is getting higher, probability of the impact is going to be higher. And if you look at the high impact one, they are very, very comprehensive and it is multifaceted, and you need to have a credible evaluation of the impact. So when you're looking at the high impact, you're looking at the dollar. Economically, you can be in big trouble. You're looking at social impact. You're looking at geographic impact. And the most important thing is the health and safety of individuals. Then, if I keep on looking at the resilience, I told you when we are looking at the resilience part of the power system, it must have the ability to limit the extent of the system impact and the duration of degradation in order that we can sustain any critical services following any extraordinary event. So, any extraordinary event that is there, your system is able to cope up with it. So, what are the key enablers that we can get proper resilience? You must be able to anticipate, you must be able to absorb, you must be able to rapidly recover from, you must be able to adapt to, and you must learn from such an event so that if such an event occurs again, you will be able to handle it. Now, these extraordinary events for the power system may be caused by natural threats, may be caused by accidents, may be caused because of equipment failures, and may be deliberate in nature. And the deliberate one, which is becoming a very big issue for power engineers, is the cyber attack. So what we have is a situation, where we are looking for the drivers. What are the change in the design and the operation in the electrical power systems, and what are the drivers over there? What is the challenge which is facing the designers and operators? Remember, we are looking at net zero power systems. If you want to look at systems of resilience, you are looking at net zero power system. Everyone is talking about net zero power system. You're talking about decarbonization. You're looking at the challenges which is coming with the smart grid. These are the ones that I'll be talking about in my presentation today. So, my first challenge, let me look at my first challenge. My first challenge is the data. My friend, data, and many people say, data is the king. You need to have efficient use and reliance on existing and newly acquired data. And these newly acquired data is through deployed local measurement devices. And there is two-way communication, which is being done by meters and global monitoring systems like WAMs for state estimation, and static and dynamic equivalence and control, which requires and looks at real-time control. Remember that word, real-time control. I want to stress on that, real-time control. So, you must be able to have an efficient data management, which means I must have appropriate signal processing, aggregation, transmission, and your ICT network has to be very reliable. This is absolutely essential for both the static and dynamic observability, as well as for the operation and control of the system. So remember, my friend, we are looking now no longer at just data, but we are now looking at data analytics. And remember, data is not information. So, the first challenge is data. My second challenge is modeling. That means I want to model not only the steady state studies, but dynamic studies too. Remember, I told you, your system is very variable. You've got all these wind generation, PV generation, you've got prosumers, you've got batteries, you've got fuel cells, you've got hydrogen, name it, and it's there. So your operating conditions are completely influenced by market forces and all the uncertainty that the generation and load brings. Now you also have clusters of renewable energy sources. That means you've got generation and storage. And these clusters of renewable energy sources of the same or different type, some of those not visible at transmission level. They could be sitting only at the generation level or at the load level. The modeling is a huge issue. Then you've got a problem with demand. How do I model the demand? Because I've got new types of energy efficient and power electronics control loads. I've got heat pump. I've got customer participation and behavioral patterns. I've got EVs, as I told you. Storage technologies. This is also a very difficult thing to model because you've got all these ancillary services. I mean, I can only tell you about my own house. I've got 6.6 kilowatt of PV, and I've got 5 kilowatt of batteries. So I want power to be, I want all the power that is consumed in my house to be produced by these new devices that I have got put in my house, on the anticipation that my electricity bill will reduce, because customers are fed up with paying all these high amount of electricity bill. I received today itself a notice from my electricity company saying that from 1st of August, my electricity bill is going to increase approximately $184 a year. Now I can afford to live like that. Majority of my people in Melbourne cannot do that, especially those who are in the low SES thing. So we've got a huge amount of interconnected networks. We've got mixed generation. We've got stochastic renewable generation. I talked about the flexible AC transmission system. You've got short and long distance power transfer. And now on the top of that, you've got high HVDC link, not only for connecting between these power transfers, but also interconnection between the renewable lines and the traditional line. So you've got this huge problem of modeling. Then I need to model an analysis and do the analysis of a very effective integration of different energy carriers. And we want it all in a self-sufficient energy module or cell. So I have got a system which is interconnected, very critical infrastructure. So this has become a system of systems. And I've got so much uncertainties, very hard to justify conventional deterministic modeling that I used to do when I was young, where I could probably do all sorts of modeling in my traditional manner. Now I have to do probabilistic modeling. So I've got a data where there's a challenge which is real-time control, and I've got now the modeling. The challenge is the probabilistic modeling. Now, if you look at it, my third, so I said data is number one, number two is modeling, number three is control. Control, this is where my real time risk limiting control comes in. I have got now huge amount of advanced controllers. I've got to design the control structure. So now I need to be dependent more on automation. So my network automation increases. I have got to design supplementary controllers. Again, you remember I talked about VAMs. VAMs, where there'll be control and stabilize the last system, including those systems which are in real time or parts of it which may vary. All this has to be done in an uncertain power transfer and load model, and stochastically varying and intermittent power electronic connected generation, demand, and storage. So you have to make a stochastic probabilistic control of systems with reduced inertia. The second problem I have of design when I'm doing the control is to look at a new control systems or structure. This is distributed in nature. So it's cooperative or hierarchical, and it is very close to the real time, and it is adaptive. So this is a system for power network which is fully integrated with all sorts of sensing devices, ICT technology, and protection. This is where my risk limiting control comes in. So I have got two things: stochastic or probabilistic control and the risk limiting control. So risk is an uncertain event, and this has an effect on at least one objective. It is the probability of something happening multiplied by the resulting cost or the benefits of it. So now data, modeling, and now control. So I've got these three issues that I need to resolve. Let us see each one of them. My first one I told was data. So as I told right in the beginning, that I need to incorporate data analytics. So if I want to do appropriate planning, operation, and control, I need to do data analytics. Look, my friend, I'm an electrical engineer by profession. I have no idea. I have no idea of all these smart aleck people who are IT, all these artificial intelligence which has come. I know my electrical engineering. So I, as a traditional, conventional power engineer, need assistance and needs help from those uh, from those from those who were who are trying to who know all these skills. So therefore, I need my workforce to be retrained, to be reskilled, and employ people who are not from engineering. I need people who are from computer science. I need people who are from mathematics. I need people who are from the communications. Don't forget, I need people from social sciences too. So that is my first problem I have got. Data analytics, I need help, and my help can come from those who are those smarty type of people who are dealing with artificial intelligence, computing, maths, comms, social science. My second problem I told you was modeling. So I have to have a strong emphasis will be put on developing appropriate, you will get appropriate and most likely probabilistic model of components, process, and events. So now for that, I need this new type of people who have got this probabilistic model. That means, again, I need new forces. I need either to retrain our people, which is hard, or reskill them, or try and get help from non-engineering people. Again, people from maths and social science. That was my second challenge I had. My third challenge I have is control. That is the new control approaches. I told you about stochastic distributed control. That means I need a greater network automation. And I told you I need it all in the real time risk limiting control. Again, to do that, I need to retrain my engineers or reskill them or employ people from outside. Again, people from control system, maths, and communication. So if I'm looking at the new grid that I'm talking about, I must be able to have people who can help me. So that was my first one. I've identified the challenges. So these are the challenges that I have. So let us see my next thing. And that is where the future grid is. Look, my friend, the grid today, the traditional grid that I have is the traditional grid that I have. Look at that. It's centralized. There's a flow of direction is going like that. Can you see? All going from one direction. Can you see the direction? All going in one direction. So the generation is just following the load, all that load. and based on historical experience. So new producers don't have any room over there. New producers do not have any room to play in this part. The new grid, the future grid, the smart grid that I have, look at the directions, is going in all sorts of directions. So it is not only centralized, but it's also distributed. Now you see, I bought in, besides these traditional power systems, I've got all new type of systems. Look, I've got renewable. These are intermittent in nature, right? I've got renewables. I've got consumers, which has become prosumers, as I told you, prosumers. So he's no longer a consumer. I've got prosumers. So it's no longer only consumers, because consumers are also producing. And look at the directions. Unlike the previous direction of the traditional grid, I have directions everywhere. Now, if you look at it, the load which is there is adapted to production. And it's all in real time. So, one thing has just become very clear. The smart grid has become a political issue. I mean, I've heard the US president talking about it, the European Commission talking about it. Everyone has got a political target. I know that the government departments are talking about it. You name it, the government departments are talking about it. Parliament is talking about it. Regulators are talking about it. You, you find the utility CEOs, boards, investment plans, support business targets. Everyone is talking, and they all want to have technical solution so that they can get a political and business target. Now the question comes, where are you and me? Where are we? I can't see us. We can't see engineers over there. But remember, don't you ever forget, you are also a consumer and a voter. So you are there, my friend. You are there. It's not only the US president and the utility CEOs and business people. You too are joining hand in hand with this smart grid. And there are so many players, and we need to make sure that there is consistency. So, my friend, if you look carefully, I have got a portfolio where there is production, where I have my traditional, as you look at it, I have my my traditional power grid. I've got solar generation, I've got wind farm. And now I've added all sorts of distributed, all these new things I've got, the solar, the wind, the distributed. Remember also, my friend, I now have smart meters, I've got smart houses, I've got plug-in vehicles, I've got industry. If you look carefully, I need to have real-time pricing and control centers. And all of them are utilizing VAMs, looking at power applications for wind or solar integration. We're looking at types of substation and feeder automation. This is where I'm doing a lot of work in IEC 61850, where I've got my own substation. I built in a $3.5 million lab. Then I've got utility communication systems, where I've got my PLCs, my optical fiber and wireless communication. Then I told you that we've got FACTS. FACTS is producing grid stability and the grid code compliance to the renewable producers. Then I've got SVC Light. Then I've got these HVDC Classic, HVDC Light. These are all ABB products which has come in. That is very efficient for long distance transmission. So I've got integration of wind and solar. I've got electric vehicles. I've got smart meters. I've got industrial energy management system. And on the top of that, I have smart houses. So if you look carefully, I told you that the network we have, here is my network, my friends. That's my network, where I have my my generation, I've got my transmission, I've got distribution, all my smart meters, and this is at the customer end, where I've got my home area network, building area network, industry area network, and all my electric vehicles, etc., my PV panels, my transmission line, my smart meters. But now on the top of that, I've got a new layer, my friend. This is the layer that traditional power engineers do not know much about. That is a smart grid comms layer. This is where you have the local area network, you've got the wide area network, you've got a neighborhood area network, and you have the same thing, the HAN, the BAN, and the EAN on the customer presence. So this is the new layer, which is as difficult and as big as the smart grid. So what are the challenges? Look, my friends, any new technology which enters in the market faces huge amount of problem. Acceptability is a very big problem. I mean, I have huge problem when I give presentation on my smart grid talk and industry. I give this many times to industry, and the industry asks me that how fast will my system become, and I say few microseconds. They say, why should we change to all these smart technology going to IEC 61850? We are very happy with DNP3. Why should we change it for few microseconds, for few milliseconds? Because we have become complacent in the power field. We have gone old in our system and we just want to retire. I tell them, if you don't change, your bosses will make you change it. Or they will bring up new force that will take up your job to do it, where the young people will be coming in. And if you don't change yourself, you will find a huge amount of problem. So there's a huge amount of regulatory systems coming in. Regulations are changing. There are a lot of utilities which are trying to overcome disincentives and create incentives so that we can have a smart energy technology. But the most important thing is that we need to train new grid technology. Remember, the workforce is aging, and there's two things that we have to solve: the comms issue and the power issue. So two critical things which is in the power industry today. So I have this thing, and I keep on talking about the growth in this new intelligent energy technology. Those days have gone when computers and communication devices were talking about 5G and power was in 2G or 3G. Believe me, we are now talking about 5G too. So we have to make our system look very smart. We have to go for energy efficient and environmentally friendly process and products. We have to empower so that there is active participant in the process. We have to provide intelligent home appliances. So we have to tell people like me who is scared of that $184 increase in my power bill from August 1st, I need to make sure that this does not have impact on me, because I will not be able to afford if there is any further increases. And many people are having problems paying their electricity bill. So you might find a situation where this was said as a joke by Ted Wade when he mentioned that, look, I will give you a free house. Can you believe you will get a free house in Australia? Provided you buy from Gateway Computers, you give Gateway Computers your utility bill, your internet access, and your telephone service for the rest of your life and your children's life. Sign a contract, you get a free house. A house which is costing $1.5 million. That is the type of situation which we are left with. And then you find that the new reality coming in. You find there won't be any more power sale by time of use. We used to call it TOW, time of use. That is daytime power and nighttime. off-peak and on-peak, as we used to call it. Now it will be based on your appliances. If you have got a 5-star appliance, you will be paying less bill than me who has got a 2-star appliance. You will find a huge amount of island of automation. There will be granular energy management. Everyone will have diagnostic. You will find your fridge. Even today, you can buy fridge at your home. I've got a fridge at my home, which tells me that my cheese is gone. I need some more milk. I need some veggies or whatever I put in my fridge. So there is diagnostics available. And the behavior of consumer will be known. And you will find that now no one will be selling electricity. They'll be selling gas. They'll be selling telecommunication. So there'll be co-marketing going all around. So if you look carefully, we have the power to transform the industry. We have got at the moment internet. We've got DER, distributed energy sources. We've got an energy management system. So these technologies are around, my friend. Okay. But I told you the system will be disruptive and we have to integrate this disruptive system. So we will have issues with reliability. We will have issues with economic volatility. There's a war going on in Ukraine, nothing to do with Australia or other part of the world. We're thousands and thousands of kilometers away, but gas supply is in huge short supply at the moment. So you will have problem with available technology. You will be, remember my friends, it'll all be based on what the business wants and what the customer wants. Okay, now what could you do? And people tell me, is the future, when is the future going to come? I tell them, no, the future is here. Right now we are in the future. Try and scan and understand the market, act, initiate, and try new technologies, develop new options, build up alliances and partnerships, leverage your advantage, and prepare for a very disruptive market force, my friend. So what can technology do? I think we need to close the gaps on technical issues. My friends, we have to demonstrate any advanced system. We have to integrate the DERs. We have to close the gap on integration. We have to look at community solution. I can't see why 100 houses in a suburb can't be having their own power supply, one community power supply, which has the big sort of battery in it, some megawatt sized batteries rather than having kilowatts of batteries, and they are supplying to the whole 100 houses in that community. And remember, policy and market rules has to be resolved too. So my friends, I am looking at a very smart grid. S is for signal processing, state estimation, stochastic generation, self-healing. A is for adaptive, augmented power transfer, affordable solution. M is for monitoring, that is VAMs, looking at multi-energy carriers, multi-variable operation, optimization and control, mixed generation, market enabler. R is for robust, responsive demand, reliable ICT, renewable energy sources. I talked about real-time control, reduce uncertainty. And T is for transcontinental, tailored for individuals, tolerant to behavior pattern and trade-off analysis. So my friends, I can see that I need to model and operate by relying on non-deterministic and close to real-time application. I told you real-time control and operation. That means stochastic, probabilistic, and computer intelligence-based model, which can handle data and methodologies and possibly offer us state-of-art VAMs, integrated ICT systems, and a very intelligent PE devices. So, in summary, what I have talked about today is that smart grids are prerequisites if we want to solve our environmental problem, energy efficient problem, and secure supply. Implementing this smart grid, remember, the grid is evolving. and smart grid is there. Many requirements are there. One is the management, outage management, and the other is the installation of HVDC and FACTS. We have got issues with integration of renewables and electric cars. We need new solutions. We need to demonstrate electrical storage, demand response, and charging infrastructure. So some sort of standardization of industry standards are required. Smart grid is a challenge, and this will be appealing to young engineers to the power industry. Now, the areas that I think you should watch, and the areas that I think you should watch, and the area is, as I told you, data analytics, probabilistic modeling, realistic control. So data, modeling, control. These are the three areas that you need to watch. Look, my friends, I wanted to talk a bit on the IEC 61850 based substation, but I'll skip that because I think I'm coming close to the end of the time. If I can be allowed to show you what I have built only, although I have a video, but I don't think I have time to do that. So what I'll do is just show. This is the room that I have got. This $3.5 million facility that I've got in my lab. These are the panels that are there. This is where I do my training to the industry and to my postgraduate students. And here is the control room, which is geographically separated. Okay, and so we have got now a whole new opportunities of building uh, smart substation, which will be very reliable, resilient, efficient, flexible, and secure. Um, just a quick one. This is the last slide that I want to talk about. And that is, although I don't want to do this, remember all that thing, that $3.5 million thing that I built, it took me about 15 years to build it. Now it has become outdated. I now have got solid state IED components. I've got solid state intelligent devices, and that is what uh, and that is what is coming in. That means I have to rebuild the lab, and hopefully I've been asked by United States to come and build that in their country. So hopefully I can do that. With that, Barry, I've completed my presentation. And yes, Barry, please go ahead. Is there any quick questions that I need to answer, Barry? Thank you very much, Vicent. Thanks a lot. Thanks, thanks, Galani. Um, thank you very much, Rujin. Thank you, Payman. Thanks, Sagar. Thanks a lot, Giovanni. Thank you, Ammar. Thanks a lot, Chris.
Thanks, everyone. Thanks,
Barry,
Prof.
I think, thank you very much, Paco. I hope once when you look at Paco, when you look at my slide, you will get more information. Thank you very much, Albine.
100%. All right.
Barry, if there is no other questions, can I be excused, Barry, and you can continue? Thank you very much, Ray. Thanks a lot, James. Thanks, Barry. Thank you, Alfred. And thank you, 71278188859. With that, I have completed my presentation. Thank you very much for listening. Thanks a lot, Galani. Thanks, Michael. I'm so glad. First of all, I must apologize. I forgot to apologize. 2 weeks back, many of you were there. Due to technical problems, I could not make the presentation. I'm very sorry about that. And I thank you very much for coming the second time. I hope I have made this presentation to your expectation. And if I've made some mistakes, please let us know. You take care and all the best.
All right, guys. Thanks everyone for joining. Yeah, this is give you some insights of our upcoming programs. So you can just always go on our website to view the course schedule. Yeah, this will be our upcoming webinar. So if you are interested in joining the session, just go and sign up on our website under upcoming webinars. Yep, this is yeah, for those who have been asking me about the certificate of attendance. So if you can just scan the QR code, or you can just follow that link, you should be able to complete a short survey form. And yeah, please note that you will be receiving your certificate of attendance in about 2 working days. And yeah, if you can scan the QR code or just follow the link to ensure that you complete the short survey. All right, ladies and gents, on that note, thank you for joining us. We came to the end of our session for today, so you can always contact us through if you have any questions, any suggestions, just feel free to message us. We would like to hear from you.